Okay, so disk method. The objective to calculate a volume created by a solid of revolution using the disk method. So I already kind of talked about this a little bit. We're going to take a function that's a solid of revolution. It's round. It's a roundish shape. Okay, that's the idea behind what we're doing today. Oh man. Here we go. So we have this function here. Look at the function y equals x squared. Okay. And what we're going to do is consider the region bounded by the function, this graph, the x-axis, and the line x equals 3. So we're considering this region here. Okay. Consider that region there. Consider rotating that region around the x-axis. That's what we get. Don't worry about it. Don't worry. We're going to come back to that screen a little later anyways. Okay, so this is what I'm trying to do is give you visual. So that's the object we're trying to find the volume of. You're taking that and spinning it around. This is what you get. Okay, this is the object that you get. Okay, now let's look at only one rectangle in our region that's rotating around the x-axis. The rectangle in this method will always be, come on. There we go. Drag it over. In this method will always be drawn perpendicular to the line we rotate around. This is important. Okay, so here's my region. I'm spinning it around this way. Let's consider one rectangle in there. And yes, get this drawing down in your notes. Okay, so you have to imagine this is part of our solid of rotation is this one rectangle. And what we're going to do is we're going to rotate that solid. That one rectangle gets rotated around the x-axis. And what do you get when you rotate that rectangle? You get a disk. Okay, you get a solid disk. And what happens when so what is the formula to find the area of a disk? The volume of a disk or of a cylinder, pi r squared h. You should know this one. You are smart people, right? Usually. Okay. Okay, then I like this. This is the banana model, the idea of what we're doing here. So you want to find the volume of a banana. What do? You break it down into parts. And so this is what we're going to be doing. Breaking it down, finding the individual rectangles, rotating those individual rectangles around, creating a disk, and adding all the disks together to get a solid. So once again, so you can see what's happening. So each one of these is a rectangle spun around, a rectangle spun around, a rectangle spun around, rectangle spun around. But when you look at this, that's not quite smooth to match the curve. So what do we need to have? Narrower rectangles. And what do we do when we add up a whole bunch of really skinny things? We do the integral. Okay. The integral pi r squared h. Okay. Turns into this. The radius portion of it is f of x. Our distance from our axis of rotation, which is the x-axis in this case, to the function, that's our radius. Our height is dx. The distance between our x's, dx delta. Remember, dx stands for delta x, our change in x. And when we have a microscopic change in x, we call it dx. That's what we're doing. So it's really actually a simple formula. Pi r squared from A to B. Pi, whatever the radius is squared, from A to B dx. Here's the things you need to figure out. You need to figure out where it starts, where it ends, and what my radius is, what the formula for my radius is. That's what you're looking for. When we did the volumes by slicing, same idea, cross-sectional area. What is the cross-sectional area? This is the same basic idea as what we did by the volumes by slicing. We're slicing it up. Only every single slice is a disk. Because it's rotated, when you rotate it, what do you get? You get a disk. It's the same thing we just did. Only instead of the slices being odd shapes, like sometimes they're triangles and sometimes they're rectangles, every single slice in the rotation is a circular disk. It's the same thing we were just doing, only every single slice is a rectangle, is a disk. Does that make sense? That's exactly what we're doing here. Okay. So let's go back and consider the function. Let's do this. Let's find the volume. I think. Nope. So we're going to do that here. We're going to find this volume of what we were talking about. Okay. So we have our region from, this is x equals 3. Okay. And we're bounded by the function, by this curve. That's a lousy drawing the curve. The x-axis and the line x equals 3. That's our region that we have. Okay. Now, because we're spinning, what axis are we rotating around? We're rotating around the x-axis. So everything we're going to do this way is going to be dx. If we were spinning it this way, we'd be doing it dy. We're rotating it this way. We have a horizontal axis we're rotating around, it's dx. If we have a vertical axis, it's dy. Okay, we're rotating it. We have a horizontal axis, so it's dx. That means our bounds go from x. So we're going from 0 to 3. So our volume is the integral from 0 to 3 of pi times whatever our radius is squared. So now I have to figure out what's the function for our radius. What's the formula for our radius? Well, if we're to draw in a little rectangle in here, remember our radius, this rectangle gets spun around, right? So our radius is the distance from here to there. That's our radius r. What is the formula? What function gives us that radius? What's our graph? What's our region? What's the function? X squared. So our radius is x squared. So it's x squared squared dx. That's the integral you do. Now, a couple of things I want to talk about. If you're doing this by hand, and this is very easily doable by hand, here's what I suggest you do. First thing you do, pull that constant out front. Simplify x squared squared is x to the 4th dx. Okay. Which means my answer is pi. What's the antiderivative of x to the 4th? X to the 5th over 5 from 0 to 3. Extend the page, which is this funky little white thing at the bottom. That's okay. So it equals pi times 3 to the 5th over 5 minus 0 to the 5th over 5. 3 to the 5th, 3, 9, 27, 81, 243. Equals 243, 243 over 5 pi, and leave it in terms of pi, dear Lord, please. Okay. If this is a non-calculated portion of the test, this is what they would want. This is how you want the answer anyways. You don't want to multiply it out times 3.14159 because you can't go 3.14 because 3.14 on the AP test is not accurate. You need 3 decimal places minimum. 3 decimal places minimum. Minimum. And at any point prior to the final answer, you better be carrying at least 5 or you will get round off error. I see students do integrals on their calculator and their bounds are decimals and they round their bounds down to 3 decimal places and their final answer is not accurate to 3 decimal places because they rounded off too soon. Carry a minimum of 5. Minimum of 5. Okay, you can always go more, never go less than 3. You can always go more. Have fun. Okay. On the AP exam, let's talk about what they have looking for that. This question would be worth 3 or 4 points. Most likely 4. Okay. 1 point for the bounds and constant of integration. What do you think I mean by the constant of integration? What's my constant? Pi. If you're doing this particular problem and you're finding a volume of rotation, pi is a necessary constant to have. You get a point for having 0, 3, and pi. You don't have the pi, you don't get that point. 0 and 3, you don't get that point. Okay, you get 1 point for that. 2 points for this, most likely. And rarely is it this sweet and easy. Okay, but usually 2 points for the integrand, minus 1 point for each mistake, maximum of 2 off, and then 1 point for the answer. And you can't get the answer point if you've missed both points here. And you can't get the answer point if you don't have the bounds correct. Or close. Reasonably close. Okay. If the bounds are decimals and you're off by a thousandth or a few thousandths, that's not that big a deal. They'll compute that. If you're off by 100th or more, they generally don't compute your answer to make sure you're close. Okay? That's just kind of how they roll. Okay. But this is what they do. And you'll see more as we're going along. Those are the things that I'm going to be looking for. Do you have your bounds? Do you have the constant of integration? Do you have the right function in there? And did you give me the answer? This is a very little partial credit test coming up. But this is what you have to do for it. Okay? Questions so far? Okay. Find the volume of a solid of revolution generated by revolving about the x-axis, the region in the first quadrant bounded by the x and y-axis, and the ellipse 4x squared plus 9y squared equals 36. So basically what you're doing is you're finding half of this because it's the x-axis and part of an ellipse. Let's say you cut a football in half. Actually, I think one of your homework problems is finding the volume of a football. It's not an ellipse. It's an ellipsoid. It's not technically an ellipse. Okay. So your first thing you must do, your absolute first thing you must do, is draw a diagram. You absolutely cannot solve these problems without at least sketching a diagram. So my regions that I have, x-axis, y-axis, or x, got this region rotated around the x-axis in the first quadrant. So it's, you have this, and then you have your ellipse. Now I'm only worried about what's going on here in the first quadrant. And I know roughly what an ellipse looks like. I don't have to be perfect. But what I do want is I do want to have where it crosses. So when x is 0, what's y? When x is 0, you get 9y squared equals 36, so y would be 2. So it crosses at 2. When y is 0, what's x? 3. When we let y equal 0, you get 4x squared equals 36. You get 3. So that's kind of what the region we're rotating around looks like. You have to do that. If you don't draw a diagram, you're not going to get these. It's just, you have to draw a diagram to get these. Now, what am I looking for when I'm trying to do this? I need my bounds, and I need my cross-sectional radius. So you have to picture in your mind, you're spinning this thing around, so you're going to get an object cut across like that, and you have a disc that goes in here. And you got another disc, and you got a bunch of those discs. So what's my radius? My radius is this distance there. Okay. So I have to stop and think, okay, what is that? Well, that's my equation, but the problem is I can't have my x's and y's mixed together. So what do I have to do? Solve for y. So I get 9y squared equals 36 minus 4y squared. X squared, sorry, thank you. Divide by 9, y squared equals, that would be 4 minus 4/9 x squared. Square root both sides, y equals the square root of 4 minus 4/9 x squared. And no, it's not 2 minus 2/3 x. You cannot distribute square root across subtraction. Right? Pythagorean theorem, 3 squared plus 4 squared is 5 squared does not mean that 3 plus 4 equals 5. There'll be a square root to both sides, and you distribute across addition. You will have 3 plus 4 equals 5, and it doesn't. Okay? So that's my equation. So what's my radius? That is my radius. Equals r. 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 Okay, so my volume is the integral. Now, here's the thing. Where do I put my pi? Can I put it inside? Can I put it outside? Inside? Outside? Does it matter? No, it doesn't matter. I like to put it on the outside, strictly from being able to make it work a little easier, but by the same token, it does not matter in the end. For me, I do that, stick it outside, so I know if I have to do anti-derivatives and stuff, I'm not thinking about it. Okay? So I go from pi. My integral goes from where to where? Where's my lower bound? My lower bound is 0. What's my upper bound? 3. And it's of the square root of 4 minus 4/9 x squared dx. Oh, look, isn't that nice? What's squaring a square root that makes it easy? How can I solve this? How can I solve this integral? Yeah, you can use your calculator for this. Remember on the test, you can do this. However, this might be a non-calculator portion of the test, in which case you would have to do it by hand. On my Chapter 8 test, you'll have your calculators for the whole test. I don't care. That is what I'm looking for. What it's equal to is of minor consequence. And there will be questions. I don't know if I have them on my test, but I know there's questions on the AP exam from time to time where they say, write, but do not solve. Once again, I said this the other day. If it says write, but do not solve, read the freaking test, because you might spend a half an hour on a question you're not supposed to be doing at all. Well, I kept working on it, couldn't get it done, and therefore you blow off the rest of the test. Okay. So, like I said, at this point, work it out. I don't care. Check your answers with other people, make sure you get it right. I'm not going to work with someone out here. Oh, here you go. Yeah. Solution to the example. That's the answer. 8 pi units. Antiderivative of 4 is 4x. Antiderivative of 4 9 x squared is 4 27ths x cubed. Evaluated at 3, evaluated at 0. Pi times 12 minus 4, 8 pi. Works out kind of nice, doesn't it? Isn't it nice how that happens sometimes? Questions? Okay, we're skipping that one. And we're going to this. Do this. What's your first step? Draw a diagram. Okay. So let's do this. So we have the x-axis, y-axis, put them up, graph the line, y equals 2x plus 3. Looks something like that, where that would be 3. The line x equals 3. This is our region here that we're rotating around. Okay, so we'll have kind of like a circular wedge kind of thing is what we're going with here. Okay? There's actually a particular name for this shape, but I can't remember what it is off the top of my head. But we're actually we're rotating a trapezoid around. Okay. So we need to know our bounds. What are our bounds? 0 and 3. And what's our radius? Our radius is what? 2x plus 3. So here's what so you want to do the antiderivative of this. There's a couple of ways to do this. Probably the easiest to actually FOIL out the polynomial and do it that way. So my volume would be pi times the integral from 0 to 3 of 4x squared plus 12x plus 9 dx. Okay. Ladies, gentlemen. Okay. So I get pi, antiderivative of 4x squared, 4x cubed over 3. Antiderivative of 12x would be 6x squared plus 9x from 0 to 3, which would be pi times 4 times 3 cubed over 3 plus 6 times 3 squared. And I'm running out of room, so I want to move this up. Plus 9 times 3 minus 0. Because I plug in 0, what do I get? I get 0. It's nice when 0 is one of your bounds. Or one, yeah, it makes it easy. So, let's see. 3 squared is 9. 9 times 6 is 54. 9 times 3 is 27. This is 3 squared. 9 times 4 is 36. 36 plus 54 is 90. 90 plus 27 is 117. So I get 117 pi. Yes. On the test, here's what I want to see. I want to see this or that, either one of those, or and that. I do not need to see the steps in between on your exam because you can use your calculator for it. And I will have the decimal approximation as well. Okay, although 117 pi Although if I multiply 117 times pi, I'll have that decimal approximation as well. I'll have both. Okay? Yes. Yeah. What's 3 cubed divided by 3? It's 9. 4 times 9 is... Okay. Okay, do this one. Okay, first thing. Graph it. Y equals the natural log of x. Looks like this. Y equals 1 looks like this. Okay. This is our region. We are rotating it. And which direction are we what are we rotating it around? The y-axis. So its mirror image will give you a solid that looks something like that. Okay. So our axis of rotation like this, our radius, remember, your radius is perpendicular to your axis of rotation. This is a close enough graph. Okay, close enough sketch to what it looks like. But your axis of rotation, your radius is perpendicular to your axis of rotation. So I'm doing this how? I'm doing this dy, which means the equation y equals ln of x won't work. I need to have it be x equals. What is the inverse of the natural log? E. So x equals e to the y. Okay, and where do I start? Start at 0 and I go to 1. My volume equals pi 0 to 1 of e to the y squared dy. Yes. Oh, y1 to y2. My bad. Sorry. We're going to call this 1 here, and we'll call that 2 there. It's not to scale. Thank you. y1 to 2. So I have pi integral from 1 to 2 of e to the 2y dy, because what do you do when you raise the power to power? You multiply the exponents. Okay. So my volume equals pi antiderivative e to the 2y, 1/2 e to the 2y from 1 to 2. Pull out the 1/2 just to make your life a little easier. Volume equals pi over 2 times e to the 4th minus e to the 1st, or e to the 2nd. And leave it like that. There is no good reason to change that. None. Okay? Yes. I got pi in my answer. My pi's right here. Oh, it says round the nearest tenth. Fine. Sorry, my bad. I didn't notice that part. Fine. Plug it in your freaking calculator and come up with a decimal. Who cares? Okay. But if you were to do it by hand, this is what you'd have. And I did not notice that, or I would just say, okay, equals. And do it that way. Okay? My bad. But here's the thing, and you'll notice, how often do we use the calculators in here? Not very often. Not very often, because if you know how to do this without a calculator, you can do it with the calculator. If all you ever do is do things with your calculator, you don't learn how to do it without. Okay, and at least half the test is non-calculated. Actually more. More than half the test is non-calculated. So if you know how to do all the non-calculator stuff, if you understand how to do it without your calculator, throwing your calculator into the mix for doing simple things like taking the integral, because that's all you're really going to do, that numerical derivative, numerical integral, graph it and solve it. There's only 4 things it'll help you with. Even on the calculator portions of the test, there's very little that it will actually make a difference on. So, no need to do that. Learn how to do it without your calculator. When you throw your calculator in the mix, it's not that big a deal. Just have to know how to do those 4 things. You can do those 4 things, you're set. Okay, and that's part of the reason why we rarely use calculators in here. So I want you to be able to do everything without them. Okay, and I'm not sure. Okay, set up, do not integrate.